it preserves structures in group. Okay, we have two groups. So we have a theta. A group may be G with binary operation. This is your binary operation. Two maybe G dash. Let me say this is times. Let me say this. This is something like this. Okay, this is the binary operations. Okay, then by homomorphism, what we mean is that now by homomorphism, we mean if x1, x2 are in G, theta of x1 times x2 will be equal to theta of x1 theta of x2. Remember, this is binary operation. In what? In G. While this is what? Binary operation in G dash. Okay. So that means homomorphism, therefore theta preserves binary operation. Okay. And therefore, it preserves also what? The structure in both G and G dash. Because binary operation is the one which determines the structure in these groups, isn't it? So, and that's why we need to know this homomorphism, because we're going to use it when we come to maps between groups where we require to preserve the structure, like in homomorphism. Okay, good. Then the topology itself as a structure. X tau, where tau the topology defined on X. Okay, so what is topology? It's like an operation, isn't it? Defined on the set X non-empty set. So you have a non-empty in first order, a non-empty X, okay, and an operation, let me call it a collection of subsets, normally called open sets, in X, okay, is said to define a topology on X, okay, provided what? Provided, and this topology is denoted by tau, okay? Tau satisfies this condition. Number one, the empty set and the X itself are all elements of tau, this collection. So this collection is so big it contains empty, it contains the entire space. Okay. 2, for any UI you pick, okay, in tau, the union over I, where I runs, okay, and I don't know. Then the union over I of this UI is also in tau. Okay. Ever arbitrary union, so I can ever leave it dash dash. Okay, arbitrary union. So that arbitrary union of open sets in I is also in I, and this is expected because why? Because it's also in tau. Sorry, this is expected because X is already in tau. So every such union will be a subset of X, and X itself is in tau, isn't it? Then number 4, the last one, that for any such union, the intersection also over I of UI is also in tau. So it contains both the union and the intersection. Now if tau actually satisfies this, then you say it is a topology on the space X. So that maybe you can calculate this.